Hello everybody. Today we talk about the interrupt. Well, interrupt and function call, like a call and return, are pretty much same operation. The difference is the call, you have a call address pointer pointing, okay, and let's talk about memory organization. The typically entire memory is organized like constant and variable, and this is going to be public variables, and you have a program and subroutine 1, subroutine 2, and interrupt 1. The name is different between subroutine. Subroutine is like you jump in there by call instruction and return to the original location. The interrupt is, on the other hand, the interrupt is the hardware interrupt. And for example, for the IBM computer, the disk revolution and the head movement is like a millisecond, and that's takes so slow for the CPUs. CPU can't wait millisecond. So typically what is happen is the CPU send out, the operating system send out the drum numbers, track numbers, the hardware information related to the database, and do something else until hard disk unit said, okay, I put hard disk head here on this drums and track number and ready to read out, and start reading and put it in the cache, hard disk cache. Then send the interrupt signal, and interrupt signal, this can be masked off or set a priority by the system. This OS does that, all the management. When interrupt come, then the program, whatever program doing, jump to this interrupt. It can have 12 different kind of interrupt or whatever, okay. Then when interrupt arrive, it does same thing as call. It does the routine. What it does is read out the data in the cache, and typically this data is like 1 page of the virtual memory, and that's loaded into the memory area, okay. So this is the program, and virtual memory area, and has some memory not used at the end, and there is a use for this memory. So this memory is when you go to subroutine or interrupt. So inside the CPU there is a disaster. You have all the register and program address, and has a data register. You need this data register, the pointing location of the data, and whatever other register. They are in the middle of doing something here before jumping to the subroutine, and that has to be saved somehow. So we use typically the end of memory area, we save here, and we call that stack. And inside the call, if you have another call, from here the call program, it's jumped to another call, so it's saved again, is stack 2. So the stack grow from bottom of the memory all the way to the working memory area, right? For example, this happened when you have a recursive program. You have a call within a call, so it's keep calling, and the program, this one call inside the call from here, come back, but it's call again, and come back and call, so and so, and this tree may grow very large. The program subroutine tree may grow very big. So this each node of the tree has one stack. Stack is entire register contents and address and data point and stuff. Okay, so this is what we have to do for interrupt and subroutine call. Now, when we do this, stack may grow bigger and bigger, eventually reach to the memory using for the normal operations, run out of memory, and that's OS send out a signal saying, okay, we reached the maximum, so we cannot do this anymore. You guys has to stop, right? Okay. So that's the way memory is used, and interrupt and call has to go. The keep all the important register the contents to the memory and start running a new program. This is a subroutine program, call or interrupt. And if it happened before you end the call, another call come in, then you have to save that again and go to the call, depend on the priority. So interrupt has a priority. This disk interrupt is pretty high priority because it's saved the cache here, and that cache content could be overwritten by a new request coming from different CPU. In the IBM systems, multiple CPU can send a request to read, and the cache can be filled out. There is a cache management. So within certain time that disk contents stored in the cache has to be read into the memory, the virtual memory area. Okay, so there is a timing factor. The difference between call and interrupt is call is within program, interrupt is hardware, and typically from I/O, and some communication, like a communication line. You have a communication line going, and here the data filled up the cache, then interrupt is generated requesting the CPU to get the data, because otherwise next connection more data come, it's gonna overflow. Okay, so this is a timing critical. So interrupt has to be processed in the middle of running program. Okay, so this interrupt and call is pretty much work same way, but it's same thing. You create a stack, and stack save all the content in the register, so you can run fresh new program, and when you finish, it's come back, restore from stack to this register and go back to the original program and continue whatever the work you are doing. Now in this process, how do you save all the content to the bottom of the memory? Okay, when the software manages it, every call or interrupt has initially have a section of the program. Okay, push, and push means each register is pushed into. So every register is stored by each push going up, and address and the data pointer is saved, and bunch of push is executed. Okay, and that's a way to create a stack. And stack is restored by pop instead of pull. You don't have to pull, it's pop up, right? So you put the register data one by one by push, and the pop is gonna get one by one. Okay, so this is software does most of the work. So every call, the program structure, you need a bunch of push and do the task, and when you finish it, then you do pop to restore, then return. Return means jump to the address where you're from. Okay, so the reason of using this stack, storing stack at the bottom of the memory, here stack 1, stack 2, is you allow nested call or interrupt. Okay, because you don't know when you are doing subroutine, you may have another interrupt, and you may create another stack and execute. The stack is always restored in order of creation. So this nested, unpredictable, many of nested call in interrupt is the reason why you use this unknown amount of memory, and all upper memory is used for program and data. So there is a certain space for stack to accumulate. Okay. Now, when you make a CPU, this operation, push and pop operation, this can be done by software, but it can be done by CPU state machine. Okay, because this gonna be much harder to do management by OS, because OS has to be running. OS is another program running. In the middle of OS running, this happen, then you are out of OS, right? Because you save everything in stack, and you're running a program, your own program. So what's happened is there's no more OS program. OS has to be the interrupt base, or you know, it's get very complicated. So some CPU architectures prepare the state machine, does all of this preparation, create a stack for you. So when interrupt arrive to the CPU, let's assume it's a time critical operation. Okay, they freeze all the OS whatever and create a stack, perform the interrupt. When finishing job, then it's returned to the original work. Then OS and other programs start working again. Now, state machine can do that to create a stack and return. Okay, but the return instruction also invoke the state machine. So it's the initial interrupt or call jump. Cause creation of a stack, and the return restore the original state. So this state machine, you need to have two opposite operations performing. Now, what's the advantage of this and disadvantage? Disadvantage is, okay, the using software pop and push somewhat flexible. This you lose the flexibility. But the time critical operation, you can just finish it up. Like when timer expired, interrupt to come in and do certain job. So what kind of CPU has a bunch of external interrupt coming time critical? MCU. These are the small CPU controlling I/O. This is preferred. You don't need to have the software to manage the interrupt. It's hardware interrupt. Now, this flexibility is required for general purpose CPU. Okay, so depend on the CPU design, the interrupt architect is different. And also MCU, who's going to write a program like nested code? Like a call instruction within the call kind of program. Okay, this is not allowed. So if you have pretty much the only one rebel call, okay, this is a requirement. One rebel call only, no secondary, or maybe depend. If you allow secondary, that's fine. And 3 interrupt, time critical interrupt. You have total 4, only 4 cases. So you don't have to go through this complication. Okay, push and pop and stuff. This kind of MCU design preferred hardware control. Stack management, and that's simplified the CPU programming way more. So in order to do that, I have several methods, and I don't get into this in YouTube, but you can think about it. It's not that difficult to think about how to do this in architect design. Okay, so I will probably mention that time to time in this YouTube series. So please subscribe. You get more information about the new architecture design of the CPU, like especially MCU. You don't have to General purpose CPU is pretty much established and not much change in this regard, but when it's come to AI, a floating point, and other type of CPU, you don't need necessarily this kind of architect. The general purpose CPU's functions, it's all different requirement. And MCU don't need this actually. It's a complicated push and pop kind of interrupt. There is a much simpler way to deal with it, quicker, much faster, of course less flexibility, because it doesn't allow the nested call kind of things. But who's gonna do nested call in MCU programming? I mean, no way, because memory size is limited and everything within tight bound of the memory size. So this is totally unnecessary architecture for the MCU and some of the CPU, special purpose CPU. Okay, so that's all for today. Please forget to subscribe so that you get more notice on the CPU architectures, electronics, digital design, and we will go back to analog design when we start talking about communication devices.